Okay, lesson 10, page 129, problem 55. You have this person's mouth, and there's this palate expander type of braces where this side of the mouth is going to be pulled to the left, and this side of the mouth is going to be pulled to the right. And basically, this is shown by two forces: a force of 21 newtons going this way, and a force of 21 newtons going this way. And the question says, find the net force of those two forces, which means find the resultant of those two. Now, you could just take the original two and put them in head to tail form and draw the resultant. But the only thing is, it might not necessarily be a right triangle. So why don't we quickly just look at that, okay? And we'll do it like the old school way of just putting it head to tail, and then we'll do it by using the more sophisticated component method, okay? So first, head to tail method. I take this guy right there, and I sketch it. No. 16 degrees like that. And then on the head of that, right here, I want to take this vector and pick it up, but I don't want to change its direction. It's just like I just want to move it over here. So I draw a little reference line right here. It should be horizontal, yes. And I can do better. Alright, that's the best I'm going to be able to do. And so then I measure down 16 degrees like this, and I sketch. And this here would be 16 degrees as well, and this would be 21.0 newtons. And then my resultant would be going, and they should meet up head to head right there, straight down. Now, if this little angle here is 16 degrees, I know that alternate interior angles are equal, so that little angle right in there is also 16 degrees. And if that's 16 degrees, then what's this big papa corner angle right there? 32 degrees. So I know the big papa angle there is 32 degrees. And I have these other two sides right there. So this shouts out law of cosines, okay? Because it's not a right triangle necessarily.
Isosceles, right?
It is an isosceles triangle.
So you use law of sines. You can get like the base angle.
Or so how would you do that?
180 minus 32 divided by 2, which is...
Oh, okay. So 180 minus 32 would be 148?
Yes. Divided by 2 is 74.
So then you know that this here is 74, and this here is 74. And then you could use law of sines to get that resultant. Okay? So what the heck, let's just go through and set that up. So we know that sine of 32 over r is equal to the sine of 74 degrees, this should be degrees, all over 21. And if you solve for r, what do you get?
11.6.
11.6 newtons. So that's one way of doing it. Do you see that method? Okay, but the truth of the matter is, that's not the more sophisticated method. Alright? That's like old school, getting back to fundamentals. Nothing wrong with that, but some people don't like to use like law of cosines, law of sines. So let's take a look at the component method, shall we? Okay, component method. Component method, what we're going to do is we're going to break each one of these down into parts. Yes? So I'm going to do it right on this diagram right here. If I take this original vector and I break it down, this original 21 Newton vector right here, I could say, look, it's sorted to the left, yes, and it's sorted down like that. And what would be an expression, without actually crunching it out, Alex, but what would be an expression for the component of that 21 Newton force to the left?
Cos of 16 times 21.
Bravo. 21.0 newtons times cosine of 16 degrees. And if you don't see that, just go through. Cosine of theta equals adjacent over hypotenuse, and solve for that for the adjacent side. And then what about, let me get this out of here.
Mr. Sintinsky?
Yes.
I have a question.
Yeah.
Didn't you put it like in a head-to-tail diagram?
No.
Oh.
When you're doing component method, you don't do a head-to-tail diagram until the very end.
Oh, okay.
Okay, when you're finding the resultant at the very end. So first you find the sum of all the horizontal, then you find the sum of all the vertical, then you sketch a head to tail of those two sums. Okay, so then I'm going to take this vector right here, and I'm going to break it down into parts. Yes, and it's sort of going to the right, and it's sort of going down like that. And what would be an expression for this rightward component?
Wait, for the left one, you should put negative.
Yes, because that's negative. It's going to the left.
So it's just positive 21 times cos 16.
And this downward right here. Oh, we didn't say it. I forgot to write it over here. It was what?
Sine of 16 times 21. Negative.
And it's negative because it's going down. And same thing with this guy right there. Now, if I take the sum of all the components in the x direction, it's going to be this piece here plus this piece here. No. And guess what's going to be the deal with those two? Zero. Because it's the same magnitude, opposite direction. So they're just going to add up to 0. The horizontal component of this force to the left is exactly equal and opposite to this one to the right. So it's like those two cancel each other out. And then the sum of the forces in the y direction, basically, it's just going to be this guy plus this guy. And since they're the same, it's really like taking one of them and multiplying it by 2. So it's just going to be equal to 2 times whatever negative 21.0 newtons times sine of 16 degrees is. And what does that come out to be?
11.6.
And then we have to take the resultant of this, and this is the sum of the y, and this
It should be negative.
should be negative. But when we find the resultant of those two, do we actually have to go and sketch a little head-to-tail diagram, blah, blah, blah?
No.
Why not?
Because it only has like y direction.
It only has the y direction. So that's the answer. So the resultant is simply 11.6 newtons, or you could say positive 11.6 at negative 90 degrees, or along the negative y-axis, or at 270 degrees. Don't bring in north or south or anything like that, though.
Okay. For the first method, why do I get positive 11.6?
That was just the magnitude, and then you would have to state the direction.
Okay.
Yes.
Does it have to be a follow-up question, or can it be a different question now?
First, any follow-ups on this?
Yeah. Well, I had a follow-up too.
Sure.
If vectors are equal, are their components aren't necessarily equal, right?
Um,
Or are they?
if you're breaking them down into horizontal and vertical components,
Yeah. Like if you have two vectors that you know are equal, are their components necessarily equal? If they're horizontal and vertical?
yes.
Okay.
Yes. If you break them down, because remember, you could break a vector down into unlimited number of components. So you could have a vector like this, and you could say, hey, that vector is equal to that much horizontal and that much vertical. Yes? But that same vector is also equal to a vector this way, plus a vector this way, plus a vector this way, plus a vector this way. So these are all components of the same vector. They're just not perpendicular components. So you can't just say in general, if two vectors are equivalent, then their components are equivalent, because not necessarily. However, if you break it down into horizontal and vertical components, then the horizontal component and the vertical component has to be those particular answers.
Okay.
Okay? All right, let me just save this here. Yes.